record. Thank you, thank you. Now I gotta share. Share. Hello, my name is Matheus Nunes. Um, and I'm presenting the lab one of constant velocity for physics 2211. Um, the purpose of this lab was to observe, record, and analyze the motion of an object moving at a constant speed in one dimension without changing direction. We had to capture a video and use a tracker software to analyze the position time and get the data to study the object's motion. Um, this this lab involves Newton's first law, Newton's second law, which is momentum principle. Um, um, in this experiment, we observed the motion of the moving object at the constant velocity, and um, let me just show you the video we had over here. Here we go. So we had a cart moving at a constant velocity along a ruler, so we could measure and track the position and time at a specific time. So let's say over here, we could measure the position of this object at time at certain time. Um, so we gathered the data at time 0.9. We observed that the position of the velocity was at 0 centimeters in the ruler. And then after 0.03 seconds, the position of the object would change. So our delta t would be equals 0.3. And so around 0.3. So 9, 6 is to 6.7. Um, and using the data we collected for position versus time, we had about linear trend for the position versus time uh position versus time graph of our object. So very much a constant velocity. And we can see that using the same graph, the same data we collected, the velocity versus time graph, we had the final position minus final velocity minus initial velocity over initial position minus initial velocity initial minus final time minus initial time. Final. I'm so sorry. Final velocity minus initial velocity divided by final time, the minus initial time, and that gave us the initial velocity, the average velocity of 0.078, and that was exactly what we observed to be the entire velocity of our system during the interval time. So initial velocity, final velocity, and average velocity was all the same. Because the table was smooth, we could assume that friction was negligible, and then which means there are no forces acting on the object in the x direction, and all of the other forces are being canceled out. So gravity force pulling down into the pulling the object downwards was being canceled by the normal force of the table. For the glow script coding, we used our initial conditions as the initial velocity, which was 0.781 in the x direction and no velocities in other directions. Initial position to be 0, the initial time to be 0.09, and point, 0.9, and the changing time to be 0.03. There are no forces acting on the object, so the force vector was 0. The velocity update formula we used was initial velocity plus force vector over m delta t However, because force factor was zero, the initial velocity, the velocity update and velocity remained the same, which was the initial velocity, the 0.781 for the entire time. For our position update, we use current position plus current velocity delta t. So at time zero, our uh, our position was zero plus initial current velocity times delta t, and we can see that ball velocity delta t at time zero. So at a specific time, it would be the position of the ball of the object plus the velocity times the change in time, which is 0.03. And these were the results. They were pretty much identical to our data. One one slight difference was that the numbers in the theoretical results was a little bit larger than our physical data, and that could be because we did assume that friction was negligible due to this the smooth surface. However, because we're dealing with real life, we know that even though the surface was pretty smooth, there is still some type of friction acting on the wheels of the car. So there is a force acting against the velocity of the car, causing the velocity not be 100% constant, but close enough to it to where the theoretical results align with the the observed data. Some what if scenarios. What if the orientation of the x-axis was swapped? In this case, the magnitude of velocity and position will remain the same, but the direction will be different, causing which pretty much means it would just be a negative sign in front of it if the x-axis was swapped to negative x, for example. So it would be just going to the opposite direction. However, the magnitude, so the speed would remain the same. And how many forces are being added together to have a net force of zero? Just two, the gravity and the normal force in the y direction. So gravity pulling down and normal force of the table pulling up. However, there are no forces in the x direction, meaning there are no frictions and no pulling force or pushing force on the car. And thank you so much for your time. I hope you have a great day and good luck grading this video.